ODSC Europe. My name is Suraj Subramanian. I'm a machine learning engineer at Meta and a developer advocate for PyTorch, which is one of the leading open source libraries for deep learning. Today, I'm excited to speak about a topic that I feel pretty strongly about, efficient AI, and how you might use features in PyTorch, namely quantization, to make that happen. Today's talk is broken up into 4 segments. First, we're going to take a look at why do we even need or why are we even talking about efficient AI. Next, we're going to work our way up in understanding what quantization is. Finally, we're going to see what are the practical applications of quantization, how do we actually use them in PyTorch, and what's a good workflow to adopt when you're looking to quantize any given model. As a data scientist, my focus is on finding the right model architecture, the best data transforms, and the hyperparameters to actually train the most performant model. Given how our field is still largely empirical, experimentation and the associated compute costs are inevitable. This cost to train the right model architecture, in my mind, was just a one-time cost, with some additional fine-tuning whenever necessary. What I totally missed was that as ML starts becoming more ubiquitous, we're going to see a lot more inference costs, and that's actually going to be taking up the bulk of all of the compute associated with machine learning. Take a look at this graph, which shows how increasing compute requirements for inference are driving up power consumption. While this graph shows data only from Meta's data centers, this trend is likely to be replicated as more and more applications go ML first. It's no secret that the best models at the moment are some of the largest ones around. Quite often, as the task at hand grows in complexity, models require more and more parameters to learn the problem and solve it correctly. And at the opposite end of the spectrum, the ML industry needs smaller models that don't compromise on accuracy. For ML to be truly ubiquitous, it needs the ability to decentralize. That is, don't just limit inference to data centers in the cloud, perform them directly at the edge. This is vital also to privacy-preserving machine learning. Returning to the core problem of efficiency, we do have a few solutions at hand. The first one, simply design AI hardware that can natively run AI software. An example is the tensor processing unit from Google. They designed this chip specifically for optimized matrix multiplications at low precision. The next fairly obvious solution is to design faster and smaller architectures. Of course, easier said than done. A great example of a success story here is the MobileNet architecture that, despite its small size, delivers pretty good accuracy on image classification tasks. The caveat is that a lot of critical applications that have an accuracy performance minimum, these smaller architectures cannot always deliver. So the previous two approaches require some fundamental shifts in the process, either the model architecture itself or the hardware that it runs on. The third technique looks at simpler approaches which compress the trained model. One of the easiest approaches in model compression is quantization, which is what we're going to be taking a closer look at. Quantization, it's not a new concept. In fact, it's been around for decades. Its roots are in digital signal processing. When you're converting an analog signal to digital, you're using quantization. Any lossy compression algorithms also use quantization. Interestingly, the same techniques work surprisingly well to compress deep neural networks. A major reason for this is that DNNs, especially the larger models, are heavily overparameterized. This gives them a lot more degrees of freedom, and therefore they're pretty robust to precision drops. So in a deep network, the parameters are typically in floating point precision. Each parameter is a 32-bit number. And when we move them to 8-bit integers, they automatically require 4 times less memory. Additionally, many chip manufacturers specifically optimize their chips for faster integer arithmetic. which gives us anywhere between 2 to 4 times speed up. The actual workhorse of quantization is the mapping function. This is what takes a floating point value as input and returns its counterpart in lower precision space. And when you think about it, even the humble rounding function is a mapping function. But typically we want more control, so we parameterize the rounding function into an affine transform. And if you look closely, this resembles a linear equation where the slope is the inverse of s and the y-intercept is given as z. Naturally brings us to the next segment of the talk, quantization parameters or Q params. So S and Z are collectively called the Q params. S is the scaling factor. This parameter quantifies the ratio of your input range to your output range. So for example, if you took values between 0 to 99, that is 100 different values, and your output supports only 5 values, let's say from -2 to 2, then the scaling factor is 100 divided by 5, that is 20. The 0 point is the offset term. It adjusts the mapping so that a 0 in the input space maps perfectly to a 0 in the output space. So now we understand how quantization works intuitively. It's pretty simple, right? There's just an affine transformation. But when we start to scale out things to the level of entire neural networks, things can start to get a little trickier. So a quick primer. Within a neural network, there are two primary candidates for quantization. The first being the weights or the parameters of the neural network, and the other being the activations or any intermediary outputs within a neural network. So let's take a look at some of the techniques to quantize neural networks in PyTorch. The first paradigm is post-training quantization, and like the name suggests, here we take a model that has been already trained using floating point numbers and then convert it to integer. Like we saw earlier, there are two things in a model that we can quantize, the weights and the activations. So in dynamic quantization, we only quantize the weights, but in static, we reduce the precision of both. So dynamic quantization is the simplest technique. Here, the weights are pre-quantized. That is, they're converted to integers offline. And as each activation comes into a layer, it is quantized online or on the fly, hence the name dynamic. So quantizing online, it consists of two steps. First, you calculate the Q params, the quantization parameters S and Z. This step is also known as calibration. And next step is the actual conversion from floating point to integer, which uses the Q params. So dynamic quantization works great for recurrent layers and transformer layers. That's because typically these modules have a lot of parameters which occupy a lot of memory. Quantizing these reduces the size by about 4 times. The simplicity of dynamic quantization comes at a cost of overhead. The activations need to be quantized at each layer. They also need to be calibrated every single time. So remember, if you're using dynamic quantization, it might be better to use smaller batch sizes, which means there's less calibration. That is, you're calibrating a smaller batch of activations. In static quantization, it adds one level of efficiency and complexity to dynamic quantization. Here, both the weights and activations are pre-quantized offline. The model is offline, there are no inputs yet, and therefore there are no activations. So how are we really quantizing this? So when we say pre-quantized offline, we mean that we're going to calculate the Q params for the activations offline. So we are only doing the calibration step offline. To calibrate it, we use data that is representative of what we expect to see in production. So some examples could be using the validation set or even real data that you may have encountered in production. So this method, it provides the faster inference than dynamic quantization because it eliminates the overhead of quantizing the activations at each layer or calibrating the activations at each layer. Caveat is that static quantization might suffer from more accuracy drops than dynamic, and this is probably because the calibrations are pretty static, and what you may have calibrated the model offline on might not be extremely representative of the data it encounters in the real world. One way around this is to keep retraining or recalibrating the model, but it generally does suffer from more degradation than dynamic quantization. So in post-training quantization, we assumed that once we have a trained model, we convert it and never bother with training again. In QAT though, we try to factor the effects of quantization into training. So it's a very quantization first, or hence the name, quantization aware training. So contrary to popular perception, QAT actually trains the entire model in full 32-bit floating point precision. It does one extra step over normal training. Along with calculating the training loss, it also simulates quantization to calculate the quantization error with those weights. When you're backpropagating in QAT, it uses both the training loss and the quantization error to converge to weights that minimize model error when quantized. So take a look at the figure on the slide. In figure A, we have the results of post-training quantization where the model has where the FP32 model given by the yellow dot has found a local minima. However, when we quantize that same model in PTQ, it moves to the blue dot, the solid blue dot, which is unfortunately in this case higher up on the loss curve. The same model, when using QAT, during training, instead of finding the most optimum minima in floating point 32, it actually finds the wider minima. When quantizing this model, the int8 loss is much lower than what we would have encountered if we were using PTQ. QAT is the most complex approach, but also the most accurate. It is also the most expensive approach in quantization compared to the other techniques. QAT tuning an existing floating point model can take anywhere around a few hundred epochs. So here's a quick comparison of how various techniques work on different architectures. So we can see that MobileNet, despite its small size, is actually performing really well in terms of inference time. We have used QAT because since it is a small model, we expect smaller models to have more accuracy degradations, and therefore we need to be more intentional about quantizing these models. So QAT was a good choice over there. Also, since it's a small model, retraining the model in QAT would not pose a significant compute cost. You can see BERT, we got a free speed up of 1.6x with no accuracy degradation. In PyTorch, there are two ways to go about quantizing your models. There's the older version of eager mode and the newer one, which is fxgraph. Fxgraph is a very automatic way of quantizing your models. It generally just has 2 or 3 function calls that you need to make, and PyTorch handles all of the quantization mechanics under the hood for you. So clearly there's a lot of options available to you when you're quantizing your model, almost enough to give you choice dilemma. But when we are going into productionizing our model, when we are trying to quantize a model for production, it helps to make an informed choice based on empirical results. And a way to do this is given by this flowchart. It uses some of the current research in quantization to determine what is the order of techniques that you should evaluate your model on. So we can take a more hands-on look at this. If you'd like to follow along, please clone this repository and open the workflow notebook. It has code for going through the quantization of a ResNet 50 model. So we're going to follow this flowchart, and I'm going to be voicing over the reasoning behind each step. The first check we want to do is whether the model is large enough. Like I mentioned earlier, larger models do better because they are over parameterized and they therefore have more degrees of freedom for us to play around with. A thumb rule is a model should have more than 10 million parameters, but as with most thumb rules, your mileage may vary. This is an active area of research, so take this with a grain of salt. Next, we want to ensure that we have a floating point trained checkpoint. So in this case, in this example, I'm using ResNet 50. I'm using a ResNet 50 model, which was pre-trained on ImageNet and then fine-tuned for CFAR. The next important check is to see if we are actually using a supported backend. So you want to quantize your models on a machine that has the same architecture that you'd expect this model to run on. Currently, we are supporting x86 and ARM CPUs. More backends are on the way. You should probably, if you're interested in this, you should track the RFC on this topic. Okay. So before we move on, let's establish a baseline for our floating point model. The three metrics that we are most concerned for are the model size, how long it takes for inference, the inference latency, and of course, the accuracy of the model. So we can see that the floating point ResNet occupies around 95 megabytes. The accuracy is 87.3. And the time it has taken to run through the entire CFAR test set is 82.5 seconds. Next, we want to take a look at what are the predominant layers in the model. Like I mentioned, dynamic quantization works best for linear, recurrent, and transformer layers. Static quantization works pretty well for just about all of the other modules. So our ResNet, if you're familiar with the architecture, it contains only one linear layer and everything else is a conv block. So dynamic quantization really impacts only a single layer in this model. So clearly, the better technique over here is to go with static quantization, but I'm going to show you what using dynamic quant on ResNet looks like too. So like I mentioned, FX graph mode makes things really simple. It's just two API calls and everything else is managed under the hood. Here I first set a quantization configuration. I'm using the default one out of the box, so I'm not touching anything. I first prepare the model with this configuration and then I convert it. So let's see how this performed. The size has remained mostly the same. That's because we are only reducing the weights of one layer. The accuracy is also about the same. The time has reduced though. It was around 82.5 seconds and now it's around 78.7. So that's a 4-second speed up. Not much, but so let's try static quantization now because we do need better performance. So I'm going to skip over this, but you feel free to download and clone this repository to go through all of the cells yourself and maybe try it out with a different model architecture as well. So similarly for static, I set the default quantization config. Over here, I first prepare the model and then I calibrate it. So I'm passing it data. So over here, there are 3 steps that I'm taking. The first one is to prepare the model for quantization. The next one is to calibrate it. That is, I'm passing it representative data for it to calculate the Q params on. And finally, it uses these to convert this FP32 model into an int8 model. So let's see how static ResNet performs. So we can see the effects of quantization very strongly with the statically quantized ResNet. The size has dropped to 24 MB, which is a direct 4x reduction. The accuracy has stayed about the same, and the time to run through the entire CFAR test set has also dropped by 2.5x, from around 85 seconds to 34 seconds. So this is pretty good, but if you're still not happy with the accuracy, there's one thing that you can do. You can disable quantization on certain layers that are more sensitive to precision drops than the others. For this, PyTorch provides a tool called under the numeric suite. What it does is that it takes the floating point model and the quantized model and compares it layer by layer. And it's trying to basically compute a metric which is the signal to quantized noise ratio, which tries to capture how much signal or information is lost when we are quantizing the model. So generally we want to identify the most sensitive layers and then disable quantization for those. So I've done that over here, and I'm disabling them over here in the Q config. The selectively quantized model performs slightly slower than the statically quantized model. So where the static PTQ model was 34 seconds, the selective PTQ is around 42 seconds. And it's also a little larger. From 24 MB, the size has almost doubled to 48 MB. The accuracy stays the same. So that didn't really help. But just for science, we are going to keep going through the workflow. So far, our best model is the static quantized one. So you have tried dynamic, you have tried static. If accuracy didn't work as well, you even tried selective static. If this also does not work and your application still requires much higher accuracies than you have got so far, it's time to bring out the big guns. You want to try out Q80 now. So although Q80 as a paradigm is pretty complicated, the code in PyTorch is still very simple. So I'm still getting the default configuration out of the box. Here I'm preparing the model. Then instead of calibrating it, I'm actually training the model. So I'm training it on the training set. One cool thing about this is that I can actually do the training on a GPU. So I don't need to be limited by CPU training. Once I do the training on GPU though, I need to bring it back to CPU before continuing the process. So I used around 120 epochs. I trained this model for around 120 epochs. This took about a couple of hours on a single Tesla GPU. Because the CFAR dataset is pretty small, I imagine it did not take longer. But if your data is more, if it's larger, or if your model is more complicated, this will take longer. So let's see how the QAT model has done. In terms of size, it's pretty much the same as the statically quantized model. So far the best. The accuracy, interestingly, has actually increased by 0.5%. And the time taken has also remained about the same as the statically quantized model. So here we get the best of both worlds. We get size and speed equal to statically quantized, but we get accuracies which are comparable to floating point. In this case, we have got it even higher than floating point, but this is a case of a free lunch. It does not happen typically. Um, it's most likely because the CFAR dataset is really simple for an architecture like ResNet 50 to converge on. Typically, we would expect accuracies to drop from FP32 levels for any quantization technique. So what's next in PyTorch quantization? I think we are really excited that FX graph mode is moving to beta. It's going to be a more stable API, and we look forward to your feedback. We are also extending support to custom backends. So we are not just limiting our users to x86 or ARM CPUs. Follow along in the RFC to keep track of progress in this space. We are also integrating more tightly with PyTorch domain libraries. So for example, Torch Vision already has a number of quantized models. Feel free to simply load them. You don't have to run through all of these steps yourself. You can just use pre-trained, pre-quantized models which are ready to run in your application. Finally, we are also working on a new paradigm called define by run quantization. So this builds on top of FX graph mode and just offers more flexibility and just a wider range of models that it can work with. Here are some resources, but I'll also share them as links in our virtual session. So that brings me to the end of my talk. I hope this was informative and hopefully it has inspired you to try out quantization in your applications. I'd love to learn any feedback you might have from using any of these techniques. If you run into issues, please feel free to reach out to me directly or on the forums as well. Thanks for listening, and I'm happy to take any questions.